Welcome to VLSI Design Lecture Series. In today's lecture video, I'll be discussing about cascode voltage switch logic. Cascode voltage switch logic seeks the performance of ratioed circuits without the static power consumption. It is normally called as CVSL, cascode voltage switch logic. It uses both true and complementary inputs and computes both true and complementary outputs using a pair of NMOS pull-down network and pull-up network, which is as shown in the figure. So in this particular figure, if we observe, we have two PMOS transistors, PMOS transistor 1 and PMOS transistor 2, which forms as pull-up network. And in the pull-down network, we are giving two kinds of inputs. One input is non-inverted inputs. The other input is inverted inputs. The pull-up network is connected to VDD line, and the pull-down network is connected to ground. It uses both true and complementary inputs and computes both true and complementary outputs, which uses a pair of NMOS pull-down network, for which we will be giving inverted inputs as well as non-inverted inputs. The pull-down network implements the logical function as in static CMOS gate, while the F bar uses inverted inputs feeding transistors arranged in conduction complements. For any given input pattern, one of the pull-down network will always be on and other pull-down network will always be off. The pull-down network that is on will pull that output to low. This low output turns on the PMOS transistor to opposite output high. We can understand this cascode voltage switch logic in detail by considering an example. For example, if this particular pull-down network is activated, so the ground logic level 0 will be transferred through this particular pull-down network, and because this particular pull-down network is connected to the gate of this PMOS transistor P2, this PMOS transistor P2 will be activated or it will be turned on because it is connected to logic level 0. As we already know, PMOS transistor turns on when its gate input is 0 and NMOS transistor turns on when its gate input is high. So when the gate input of this particular PMOS transistor is turned on, or when the gate of this particular PMOS transistor is 0, this PMOS turns on and there will be a connection established between the source and drain terminals of this PMOS transistor, and hence the output will be routed. In the similar way, if this particular pull-down network is activated or it is turned on, the logic level 0 passes through this pull-down network and ultimately it reaches P1 gate of PMOS transistor P1, whose logic level will be equal to 0, and hence P1 will be turned on. So once P1 turns on, there will be a connection established between source and drain terminals with respect to P1, and we'll get output with respect to Y bar, high output with respect to Y bar. So this cascode voltage switch logic can be easily understood by considering an example. So let us consider an example where both NAND gate as well as AND gate is implemented using cascode voltage switch logic. Let us consider this example. So in this example, if we observe, we are using two pull-up networks, P1 and P2, and two pull-down networks. For one of the pull-down network, we are using non-inverted inputs. For one more pull-down network, we are using inverted inputs. Ultimately, pull-down network is connected to ground, pull-up network is connected to VDD. Towards the right-hand side, the output which we get is NAND gate output A dot B the whole bar. Towards the left-hand side, the output which we get is AND gate output A dot B. We are using two PMOS transistors P1 and P2 and four NMOS transistors N1, N2, N3, and N4. The gate terminal of N1 is connected to A bar. The gate terminal of N2 is connected to B bar. The gate terminal of N3 is connected to A. The gate terminal of N4 is connected to input B. So we already know the truth table with respect to AND gate and NAND gate. With respect to AND gate, when both the inputs are high, only then the output will be high. For all other cases, the output will be low. For NAND gate, it will be exactly reversal of AND gate. When both the inputs are high, the output will be low. For all other cases, the output is high. So we have to verify the functionality of the circuit which we have discussed. For that, let us consider the first case. When A is equal to 0 and B is equal to 0, A bar will be equal to 1 and B bar is equal to 1. As we have already discussed in all our previous lecture videos, we already know that when the gate of PMOS transistor is low, PMOS transistor turns on. When the gate of NMOS transistor is high, the NMOS transistor turns on. Turning on is nothing but establishing connection between the source and the drain terminal of the MOSFET. So because A is equal to 0 and B is equal to 0, N3 and N4 are off, whereas because A bar is equal to 1 and B bar is equal to 1, N1 and N2 is on. So it looks somewhat similar to this. N1 and N2 MOSFETs are on, whereas N3 and N4 MOSFETs are off. So when N1 and N2 MOSFETs are on, there is a connection established between source and the drain terminals of MOSFETs N1 and N2. Whereas because N3 and N4 MOSFETs are off, these two MOSFETs, the source and the drain terminals are not connected. That means N3 and N4 MOSFETs act as open switch, whereas N1 and N2 MOSFETs act as closed switch, which can be understood with the following figure. So because N1 and N2 MOSFETs are on, it acts as a closed switch, whereas N3 and N4 MOSFETs are off, it acts as open switch. So under open switch condition, there will be no flow of logic. So we can discard this particular part of the circuit. Whereas because N1 and N2 are turned on, it acts as a closed switch. That means there is a connection established between the source and the drain terminals of the MOSFETs N1 and N2. Hence, logic level 0, which is ground, it will be connected through N1 and N2. The logic level 0 passes to output A dot B. That is, for the first case, when both the inputs are low, the output is low with respect to AND gate. We get 0. So when this particular side of input is 0, the output Y is equal to 0 at this particular point. This particular point in turn is connected to PMOS transistor P2 gate. So when gate of PMOS transistor P2 is low, PMOS transistor P2 turns on, and there is a connection established between the source and the drain terminals of P2, and hence logic level high will be transferred towards the output side, towards the drain region of P2, and hence the output across the right hand side, which is an AND gate output, will be equal to 1. So according to the truth table, we already know that when both the inputs are low, AND gate output should be 0 and NAND gate output should be 1, which we are getting. So the first case is satisfied. Similarly, if we consider the second case, when A is equal to 0 and B is equal to 1, A bar is equal to 1 and B bar is equal to 0. So when this happens, MOSFET N1 is on, N2 is off, N3 is off, whereas N4 is on. The MOSFETs which are on act as closed switches, whereas MOSFETs which are off act as open switches. So because N3 is off and N4 is on, this complete circuit, this path can be completely discarded because logic level 0 cannot pass through this because N3 is open circuited, open switch is there. There is only one possibility that the logic level 0 can be transferred, that is logic level 0 or ground can be transferred from N1, that is the only path, and it reaches to this particular point, which is in turn connected to A dot P, whose output will be equal to 0. So when A is equal to 0 and B is equal to 1, the AND gate output should be 0. We are getting 0. This particular point is in turn connected to the gate terminal of P2 MOSFET. So when gate terminal of P2 MOSFET is 0, this P2 MOSFET is on, and hence there is a connection established between the source and the drain terminal of the MOSFET, and the logic level high will be transferred towards the drain region, that is the output region, and hence for the NAND gate, output is equal to 1. It ought to be the whole bar. The output is 1. This particular 1 logic, this in turn is connected to P1 MOSFET gate. So when the P1 MOSFET gate is high, as we already know, when the MOSFET's PMOS transistor gate input is high, it turns off. So this P1 is completely off. There is no connection established between the source and the drain terminals of this P1. Hence, when A is equal to 0 and B is equal to 1, we are getting AND gate output as 0, whereas NAND gate output as 1. Third case, when A is equal to 1 and B is equal to 0, A bar is equal to 0 and B bar is equal to 1. And hence, MOSFET N1 is off, whereas N2 is on. MOSFET N3 is on, whereas N4 is off. If we observe here, because MOSFET N3 is on, it acts as closed switch. N4 is off, it acts as open switch. Because here we have open circuit condition, this logic level 0 cannot pass through this path. Hence, this path is completely neglected. It is not at all considered. Whereas there is only one possibility that the logic level 0 can be transferred. Logic level 0 can be transferred through the path N2 because there is a closed circuit condition established here. It transfers like this and it goes to this particular point. That point in turn is connected to the output of AND gate. So when A is equal to 1 and B is equal to 0, the output of AND gate is 0. This particular point is in turn connected to the gate terminal of P2 MOSFET, which in turn is 0. So P2 MOSFET will be on. There is a connection established between source and drain terminals of P2. It acts as a closed switch and logic level high will be transferred towards the output side of NAND. So A dot B, the whole bar output is equal to 1. And because this output is 1, the output of this particular NAND gate is connected as input gate terminal to P1 MOSFET. If the input gate terminal of P1 MOSFET is 1, P1 is off. Hence, there is no connection established between the source and the drain terminals of P1. It is completely off. So when A is equal to 1, B is equal to 0, the output of AND gate should be 0, output of NAND gate should be 1. We are getting that. Finally, when both the inputs are high, when A is equal to 1 and B is equal to 1, the AND gate output should be 1, whereas NAND gate output should be 0. We'll see whether we'll get that or not. So when A is equal to 1 and B is equal to 1, A bar is 0 and B bar is 0. So under this situation, N1 is off, N2 is off, whereas N3 is on, N4 is on. N1 and N2 are off, it acts as open switch, whereas N3 and N4 is on, it acts as closed switch. So because N1 and N2 are off, logic level 0 cannot be transferred to this particular point because both are open circuited. Whereas N3 and N4 are on, it acts as a closed switch. Hence, logic level 0 can be transferred through this path. And hence, the output here will be equal to 0. That is, the NAND gate output will be equal to 0. This output of NAND gate is in turn connected to the gate terminal of P1 MOSFET. So when the gate input of this MOSFET is given as 0, this MOSFET turns on, P1 MOSFET turns on, and there's a connection established between the source and the drain terminals of P1 MOSFET, and hence logic level high, logic level 1 is transferred to the output section of AND gate. So A dot B will be equal to 1. And ultimately, the output of this AND gate is in turn connected to the gate terminal of P2 MOSFET. So when MOSFET's input, gate input is equal to 1, that particular MOSFET will be off. PMOS will be off, and hence there is no connection established between source and the drain terminal. It acts as open switch. Hence, when A is equal to 1 and B is equal to 1, we have to get the AND gate output as 1 and NAND gate output as 0. We are getting that. AND gate output is 1 and NAND gate output is 0. This is how we implement AND as well as NAND logic using Cascode voltage switch logic. I hope that you have understood this video. Thank you.